I finally had the courage to look at this problem again. This is a very strange and intimidating problem introduced during my studying at the Grace Hopper program. I didn't solve this problem. Our amazing ex-fellow Chloe solved this in 2 hours. It'll probably take me a week to solve this. So I will try my best to explain the solution. You're an industrious programmer that lives off the grid. The local well that you use to fetch water has gone dry, so you've decided to collect rainwater to filter. However, your collection device isn't flat. Given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water your collection device is able to trap after raining. So the bricks are represented in an array, and the number of each element represents the height of each brick. So if we have an array of bricks right here, the blocks of water we can collect is 6. Because if you look at the diagram, the blue area is where the water gets trapped. They're in forms of squares. So we have 1, 2, 3, 4, 5, 6. Basically, the water is collected, held in place in between bricks that have a height of at least 1. The water will only have volume when the walls surrounding it are equal in height and at least 1 brick taller than the space next to it. We can call them bounding walls. So at the first and the last index, the water will not be collected because there isn't anything on the left or on the right that satisfy those conditions and hold the water in place. Let's look at the relationship between the bricks and water. This diagram I drew may give you a better idea. The first block of water is collected when the height of the current brick, which is 0 because there is no brick, is subtracted by the height of the brick on the left. So 1 minus 0 is 1 block of water. The second block of water is collected when the height of the current brick, which is 1, is subtracted by the height of the brick on the left, 2. So 2 minus 1 is another 1 block of water. The third and fourth blocks of water, however, are collected by subtracting the height of the current brick, which is 0, from the height of the taller brick next to the brick on the left, which is 2. So 2 minus 0 is 2. We have 2 blocks of water. The fifth block of water is collected by subtracting the height of the current brick, which is 1, by the same height of the brick from the previous calculation, which is 2. So 2 minus 1 is 1. Then the last and sixth block of water is collected by subtracting the height of the current brick, which is 1, by the height of the bricks around it. It's either the left or the right, which is 2. So 2 minus 1 is 1. We then add all the water block numbers, and that gives our final result, which is 6. The second number in the subtraction equation is the number in the array, which is very easy to get. The tricky part is to get the first number in the equation using a function. How do we do that from the array that's given to us? We can achieve that by first iterating through the array backwards. For each iteration, store the higher number between adjacent bricks in a new array. We then loop over the bricks array from the front, this time getting the higher number between adjacent bricks, and store the value in a variable called left max wall. So in the diagram, I represent the right side wall with red. So for each iteration, you can see that we carried over the higher number of the brick from back to front. And the left side wall is represented by green. Same thing, we carried over the higher number of the bricks for each iteration. So the lower number between the two bounding walls, which is the right side and the left side, is the first number in the subtract equation. To implement that in function, the function takes an array of bricks. We iterate through the array backwards. For each iteration, we pick the higher number between adjacent bricks, store that in a variable called right max, and then store that value in the array called right maxes. Then we iterate through the array from the front. This time, we pick the higher number between adjacent bricks and store that value in a variable called a left max. And at the same time, we're iterating through the array right max walls that we defined earlier. For each iteration, we compare the values left max and the right max. We pick the lower number between these bounding walls, and that is the first number in our equation. And the second number is the number in the array. So we get the result from the subtraction and add it to the total volume of water collected. Return that number, and that is our final result. If we run the function, this is basically the array of max right wall right here. And for each iteration in a second loop, this tells you what is the right max wall and what is the left max wall. So these two numbers are the bounding walls. And we pick the lower number between the two. And finally, this is our total volume of water collected. The time complexity of the solution is O of n. I listed the time complexity for each step. So for loops, it's usually O of n because we have to iterate through each element in the array. And for defining variables, it's usually O of n. And inside the for loops, mathmax is O of 2 because we have to pick the bigger number out of 2. Then to reassign a number is O of 1. And because these operations are inside the for loops, we usually multiply the number inside the parentheses altogether. So we have something like this. And we add all the steps together. We get O of 5 plus O of 4n. Then in big O notation, we normally ignore the constants. So that gives us O of n. The auxiliary space of the solution is O of 1 because we aren't creating more memory by iterating over the array. The space complexity, however, is O of n, where n is the length of the array.